3M, we're on lesson 8 of exponential equations, and we're going to use some real-life examples to determine some equations of exponential growth or decay. So we're going to do one together, and then you're going to do a few in class. This one is about chemistry. At the turn of the last century, scientists discovered that certain naturally occurring substances emitted invisible and penetrating radiation. In such substances, the nucleus spontaneously undergoes a rearrangement that may include the ejection of some nuclear particles and possibly gamma rays. Strontium-90 is such a substance. Below is a set of measurements for the amount of strontium-90 remaining after several time intervals have passed. They haven't told us how long a time interval is for strontium to decrease so much. It just says number of time intervals. That could be every month they measured it, or every week, or every 1,000 years. We don't know. Okay? But we do know at the beginning of the story, we had 500 milligrams. Finding the first differences can help us determine an exponential growth or decay equation. Usually first differences tell us whether something's a line or not. But this particular example, when you have something decreasing in the same way over and over again, would be exponential growth or decay. This one is going down. It's going to be exponential decay. Our first differences are going to help us get there. So going from 500 down to 241, we have gone down by 259 milligrams. I just subtracted those two numbers. Going down from 241 to 112, I have gone down by 129 milligrams. 112 to 61 is 51. So we're not going down by as much each time. But if you look at the numbers, they kind of look like they're close to half each time. So it certainly looks like exponential decay, doesn't it? Going from 61 to 30, we have gone down 31. From 30 to 18, we've gone down 12. And from 18 to 13, we've gone down 5. These first differences can help us find our ratio, or our B, our base of our exponential equation. I am going to divide subsequent values. So 129 divided by 259 is 0.498. The next two, 51, notice negative divided by negative is positive, so I'm not writing it down. 51 divided by 129 is 0.395. 31 over 51 is 0.61. 12 over 31 is 0.39. And lastly, so I can move this, there we go, 5 over 12 is 0.42. So true to real life, it's not the same number each time, but it is certainly a little smaller than half each time, except for that 0.61. That one's a little bit odd. These two are very similar, the 0.395 and the 0.39. 0.42 and 0.49, a little bit different. In the midst of all of that, approximately 0.4 seems to be that ratio that we're going down each time. Noticing it is not very perfect. But our rate of change seems to be 0.4. That is definitely exponential decay. The initial amount that I started with was 500. And my x is my exponent, and it stands for the number of time intervals. I still don't know what that is. So A is the amount of strontium. X is the number of time intervals that have occurred. 500 is our initial value, and 0.4 is very approximately the ratio of decay. Develop a model. Using the model, estimate the amount of strontium-90 remaining after 15 intervals. So after 15, it is going to have gone down an awful lot. So I need to type that into my calculator. 500 times decimal 4 to the power of 15. 500 times decimal 4. This is a very tiny little number. I don't know if your calculator will have what I have. I'm going to write it down and explain it. 5.37 times, and it has e to the negative 4. That's scientific notation, and it means your decimal place is actually 4 to the left of where we wrote it. So 4 to the left. 1, 2, 3, 4. Decimal 0, 0, 0, 5, 3, 7 milligrams left after 15 time intervals. Not very much at all. Using the model, estimate when there will be 0.5 milligrams of strontium remaining. So it is asking us to answer the question, when is the amount 0.5? So we need to solve the problem. When is 0.5 equal to 500 0.4 to the x? What we do know is that after 6 time intervals, there was 13 milligrams left. And it's less than halving each time. So what would be a good estimate for our x value? At this point, the tools that we have really are to play on a calculator or to do guess and check. What would make the most sense for x? Well, I think perhaps after 12 time intervals, we could have 0.5. So let's see what I get. 500 times 0.4 to the 12. Let's see if I get this answer that I think I'm going to get. 500 times 0.4 to the 12 is decimal 008. Way too small. I wanted 0.5. So let's change my guess to 10. 0.4 to the 10. You wait. Next year we have some neat strategies to try. 500 times 0.4. 10 time intervals have passed, decimal 0.5. Approximately. So we take a reasonable guess and then check our answer till we get there from here.